computer. Okay. Okay, I think it's starting, right? Good, okay. Okay, let me share my screen. Okay, so as you know, as you remember, I think most of you remember now the heat conduction equation and the convection equation, right? Let me write it here. So Q equals negative K A, okay, delta T over delta X. Let's assume the area is constant. Okay, so we can do that. And Q convection is HA T surface minus T infinite, right? Okay, okay, here delta T, you can also see, this is also delta T basically. You have a temperature difference driving the heat transfer, right? Now you know all the heat transfer you need to have temperature difference. Okay. So one time a student asked me, hey, what if, you know, I have a convection, I have a fan, you know, blow air to me. Okay, let me see my participant in case somebody join, I can admit them. Okay, what if, you see, what if, you know, I have a fan blowing to me, okay? If the ambient temperature, it's in a really hot summer, okay? The ambient temperature is like, air temperature is 98.6, okay? So will you feel any cooler, any more comfortable when the fan blowing it to me? A fan without any vapor or without any refrigeration, okay? Just a fan. You blow air to me, to yourself, you blow air to yourself, and the air temperature, hey, it's the summer, 98.6, 99, it's normal, okay? Will you feel any cooler, any more comfortable by doing this? There's a practical situation, right? Indeed, sometimes happens like this. When I would grow up, we don't have air conditioning in my house, okay? When I was a kid, in the summer, you know, 99, 98 degrees, normal, okay? I turn on the fan. Maybe that's a placebo. If the fan's on, I'm supposed to feel cooler. Is it really will make me feel cooler if that's the situation, just by turning on the fan? Anybody?
I guess it depends. I mean, if you look at it's convection.
Mm-hmm.
But if there's no difference between the outside and the surface temperature, that's zero. So zero times whatever your H is, it doesn't make a difference.
Yeah, believe in math. Okay, you're an engineer. Okay. Don't believe your intuition or whatever guess you feel it's more reasonable, or but believing the equations the previous engineer developed for you. Okay, based on that equation, okay, there's no delta T. Your ambient temperature is same as your body temperature, so there won't be any heat transfer happening, even if you turn on the fan, blow air to you. Okay, it doesn't help. Okay, okay, so okay, be careful on this. Okay, sometimes you don't have a heat transfer. Okay, if you don't have heat transfer, you won't feel any cooler. You won't feel any more comfortable. Okay, that's why in reality they put vapor on the fan, right? Is that right? You put vapor. Okay, that make much difference, right? You have a vapor that's cooler, first of all, and it carry the cool temperature. Okay, so the heat transfer totally different. Okay, it's not the simple convection anymore. Okay, so that's the reason, right? They put the vapor. Sometimes the cool air coming out there, you feel. Okay, same thing for the conduction. If you don't have a temperature difference, no matter how you know how big your conductivity is, no matter how heat transfer surface area is, there's no heat transfer if there's no temperature difference. Okay. Okay, so this is the equation, but today we are going to introduce something called thermal resistance. Okay, so we can solve heat transfer problems using a similar idea in the, what you learn in the circuits. Okay, in parallel, in series, you know. So some of the problem you have in the insulation business, you have multiple layers of insulation, for example. So if you have 3-4 layers, if you go through those conduction equation to calculate, it will be pretty tedious, right? So we are engineer, right? We try to make the problem solving a little bit more easier. So people introduce an idea, a coefficient or whatever, we call it thermal resistance. What thermal resistance is this? So basically it says Q equals to delta T over a thermal resistance. Okay, let's say TH. Sometimes people using a R value that's totally different. Okay, let's say RTH. Okay, so in that sense, in the engineering book, maybe you can just put down, now engineering book probably still need R value, but for the calculation purpose, seems like easy. If you can determine a thermal resistance explicitly, separately, then the problem, you know, if you even write a program, write a calculation program in computer, it's easy to do if you can just import a R thermal resistance, then it can calculate it by an easy way. Okay, so the goal is to separately determine the thermal resistance. But so in that sense, look at these two equations. If you use the idea of thermal resistance, what does the thermal resistance equals? In conduction, it equals what? Okay, the one thing is we want to get rid of the negative sign here. So if you want to use thermal resistance, you make sure your delta T always positive. How to make delta T positive? You use the starting temperature minus the ending temperature, right? You have two surfaces, right? Start minus the end. So it will be positive, okay? Initially, when we do this conduction equation, we use ending temperature minus the beginning temperature, right? So let's switch it. So to get rid of the negative sign. So it will be what? Anybody? So delta X, right? Divided by K and A. Okay? How about for the convection? One over HA. Okay, so I think this is the process. Okay. So the conduction convection now share the same equation, which is this. Okay, is that good? Right, we don't have to remember the two different equations. So we just, this delta T divided by thermal resistance. Okay, then it's different to calculate thermal resistance for the conduction and for the convection, basically. Okay, so just remember this, delta X divided by Ka, that's the conduction. 1 over HA, it's a convection. Okay. So if you have a problem like this now, down a little bit. Now there will be the overall thermal resistance. For example, you have 3 layers. 3 different materials. K1, Ka, Kb, Kc. Okay. Okay, previously you probably already practiced some of the homework, some of the problem in the textbook. You know, okay, solving this, we're gonna get Q equal to Q, QA equal to QB, Q equal to QC, right? You have T1, then you can find the interface temperature between A and B. Then you can find the interface temperature between B and C, okay? Because the Q is the same, right? So then you can solve the total Q, something like this. Okay, or you solve the temperature, interface temperatures, okay? So we can still apply the overall equation. Now we have this new equation, delta T over R theta. So it will be summation of R theta, okay? So does that look easier for you? I think to me it's easier, right? What is the delta T? It's T1 minus T2. Be careful, always higher temperature minus lower temperature now. So it will be R thermal resistance A plus the thermal resistance of B plus RTH of C. Summation. Why is that? Okay, it's like the serial layout in the circuits. So we name it even R, right? Resistance. You see in the circuits, you guys talk circuits, right? Circuit should be way early, right? In the maybe first or second year, okay. So in circuits, right, you have an R, right? Then you have what, current? There are three things in the circuits. Current, the ampage, amp, right? Current, the resistance, what else? What's the other one? Forgot? Circuits, resistance, current, and the voltage, right? Okay, this is in series, right? So the resistance can add together. So it's comparable to the heat transfer. The thermal resistance is the electrical resistance equivalent to, right? Not equivalent, you can compare to, right? And the Q, heat transfer rate, is the current in the electrical circuits. Okay, then what else? Temperature. That's the voltage, delta T, it's your voltage. Okay, so it's a similar logic. So then this is the equation. You can have the thermal resistance. So what is the thermal resistance of A? That's easy, right? Just remember this. This is delta AX, which is the thickness. This is thickness, let's say LA, LB, LC, the lens thickness, right? So it will be LA divided by KA times the area, cross-section area. In this problem, A is the same. So thermal resistance B will be what? LB divided by KB times A. Same thing for the C, right? That makes sense? So you basically solve the problem by giving out this equation, okay? Then you can figure out the thermal resistance, so you can figure out the Q easily, okay? Do you like this? This is a better way, right? Than what we did in the chapter 1. This is what engineers like to do, engineering way, okay? You always separate into, so if you can group many terms into a coefficient. In this case is the thermal resistance, okay? So what about, this is in series, right? In serial configuration, 1, 2, 3. So 1 resistance, 2 resistance, 3rd resistance, right? In serial. How about in parallel? Let's say you have a heat transfer going through an insulation, let's say A, B, and C. The whole surface temperature T1. The whole surface temperature is T2. Okay, we never see this kind of problem before, right? In chapter 1, okay? Because with the knowledge in chapter 1, we can do it. Now, you know, these 3 installation A, B, and C, they are in parallel. Okay, so now it's your job. One of your tasks now is to draw the circuits to solve the problem. Thermal circuits, heat circuits. Okay, so what does this circuits look like? You have 3 lead resistance here. Okay. RTHA, right? RB, RTHC. Okay, so what is the heat transfer going through this surface? Again, that's the basic equation. So T1 minus T2 divided by summation overall thermal resistance. But in this problem, hey, how do you calculate the overall thermal resistance? They are in parallel.
One over the values?
1 over what? So in the parallel,
one
yeah.
over RA, 1 over RB, and then so on.
No, 1 over R, yeah, it's this, right? If you remember it in the, is that right? Does that look familiar to you? I think you did a lot of in-circuits class. You probably forgot, right? Okay, is that right? So then you have a procedure now. If you see a parallel setup, you have a procedure now. To find the, first we just to find the overall heat transfer, overall thermal resistance. Okay, just using this rule. But do you know RTHA, RTHB? Oh, that's loud. Right? It's just the thickness. I think it's probably the same. Times what? K. Right. Okay? KA, KB, KC. Okay? Does that make sense? Is that good? This is nothing new here, okay? But yeah, I think this is the new. This is the parallel setup is new to you. But this total, the idea of the thermal resistance is nothing new. It's just a transformation of the equation, okay? Make the equation look different, okay? But in the practical application, it probably you will feel a little bit easier by doing this, okay? Plus for the parallel problem, previously, maybe it's very difficult to do. Now we can easily do it. Okay, so is that good? Right, that's the key of chapter 2, the first part of the chapter 2. Then we will look at the cylindrical coordinate. I'm probably out of time today. Then we will look at the cylindrical coordinate, the equation for the thermal resistance. Then they also have a overall heat transfer coefficient. It's not convection heat transfer coefficient. They use overall heat transfer coefficient to represent the complicated system, but the overall, if you have a coefficient, okay? And we will talk about it next time. But for today, we just try to introduce this. Okay. Now, any question before I give you the first quiz?
Someone put something in the chat.
What did you say? I'm sorry.
Someone put something in the chat.
Oh, let me see. My chat is off. Okay. Oh, somebody is coming in, right? Is that waiting? Okay, no. Okay, let me stop sharing my screen first, then we'll see the chat. Okay, now I see the chart. Okay, taking quiz another day might help. Most of the course I'm using through mobile might not be able to use GroupMe. Try your best. Okay, I think that's it. You try to catch up. And this one, if you don't take, you won't lose anything. For those, if you take, if you get a good score, you basically like extra. Okay, so it doesn't matter. It's a test quiz. I want to see how it goes. Okay, so right now, let me copy the problem in GroupMe. Okay, you will see. Okay, and please prepare a paper. Okay, write your answer on that. Then I would right now I'm going to Moodle and open the submission site, and you will see after you finish writing on your paper, you will see it. Okay, so then you will be able to submit the picture file. Okay. Okay, I sent the problem to you. Did you see it? Okay. Please also look at if you some information. It's an open book, right? So you can see all the textbook, all the file I sent it to you in the GroupMe. Everything I sent it to you in the GroupMe also may be useful. Okay, to answer this question. Okay, go ahead. You can start. I will turn off the submission site at 11:55. Okay, so I'll give you extra 5 minutes. Okay. Or you can just send me through GroupMe. Just text me individually and attach that picture in the file. Then I will see the time you submit to me, and that should be good too. Okay, is that okay?